we are going to now begin in take a look at some of the final bits to get this model fully operational and linked in with weight, with health outcomes. Okay, and as time allows, we may take it one or two steps further and explore some other issues with it. Okay, so ladies and gentlemen, we are going to go to person, and what we're going to do is to elaborate a little bit the theory of personhood with respect to a person, to incorporate weight. Okay, and with respect to this, we are going to actually introduce elements of a hybrid model. It makes it very easy to represent, and it will be convenient. It also links conceptually with some very nice modeling that's been done by Kevin Hall and collaborators, including as intramural research at the NIH concerning weight dynamics, change of body weight composition, as a response to energy intake and energy expenditure. Okay, so ladies and gentlemen, for this final piece of the model, it's going to be modest in size but important in implication. So I would like you within person, well actually I should probably save this as version 3, and really I should upload my model. It's going to be again days as the model time units and say version 3. Okay. Does anyone need me to upload my version 2 model right now so you can use it? Would anyone like that? Okay, I'll be certainly posting it afterwards. Okay. Okay, just let me know if you would. Okay. Okay, version 3, ladies and gentlemen. We're going to go over here to the right of not seeking food. Okay, sorry, the seeking food state chart. Right? Food procurement state chart. Food procurement state chart. Okay, we're going to go over to the right of it, and we're going to drag in a representation of people's weight as a continuous quantity as it evolves over time. And it turns out that there's a long tradition in physiology of using ordinary differential equation models, compartmental models, system dynamics models to characterize physiological processes. It is theory-based. Much of it has been informed by laboratory experiments and very careful measurements. And it turns out that that's true also for weight. Okay? And there are some very nice models published in the literature. We have a very nice weight model that was contributed by Kevin Hall from the NIH, which we have in AnyLogic. I would like to drag in, we're going to keep it extraordinarily simple here. So we're going to have a stock called weight in kilograms. Now a stock represents, ladies and gentlemen, an accumulation. An accumulation that's going to be influenced upwards by a flow in of energy. So this is going to be a flow in that it's going to be called energy in. Okay, energy in, or energy, perhaps we'll call it energy intake. Okay, and then there's going to be a flow out that there's going to be called basal energy expenditure. Okay, basal energy expenditure. Okay, basal because we're going to be examining, as time allows, the incorporation of physical activity as well. Okay, ladies and gentlemen, I would like you now to create here a parameter that is called energy expenditure coefficient. Okay? And that parameter will be linked to weight in kilograms.
Do you need
Yes.
The parameters that under these different menus, are they actually exactly the same?
They're the same, yeah. So it's a great question. Within the palette, you'll be able to access certain building blocks for any logic, certain components from several different palettes. And so, for example, a state chart functionality can be obtained from the state chart palette, or it can be obtained from the agent palette. Parameter can be obtained from the agent palette or from the system dynamics palette. And there's some other examples, I believe, as well. Yes, markup, for example, which by convenience are made accessible via multiple palettes. And it's a matter of convenience for you to use them. Okay? So, ladies and gentlemen, the energy expenditure coefficient here should hold a value here. Energy expenditure coefficient should hold a value of 0.02. Okay? And a default value of 0.02. Arguably, it should really be a constant coefficient rather than something we need to tell to each person, but we could examine the impact of variability in it. And the formula for basal energy expenditure flow, this flow out, ladies and gentlemen, here, the flow out here will be associated with a formula that's given by weight in kilograms times energy expenditure coefficient. Now, a couple of pointers for those trying to assemble this. The first thing is that when you try to drag something in, I'm just going to illustrate this. When I try to drag something in, I'm going to actually talk in this. Okay? So, oh, I missed it here. And no worries, energy intake here. I can actually drag this guy over atop this till it's green, and it'll be connected properly. Okay? The second thing is that you will need, and as a matter in system dynamics, we use the linkage between these things as an indication of what depends on what. So to indicate dependencies. So this flow here depends on these two quantities here, and hence there are arrows linking one to the other.
Looks like you have a battery.
Oh, am I? Yes, you're right. Thank you. It has been
Fading slightly.
fading. Yeah.
Okay, I'll see if I can get you some extra ones in the meantime. Can you use this?
Sure. Oh my gosh. Okay. Maybe you can get this when you go.
I probably could. So I'm gonna set this down here for a second. Sorry, everybody. Here. Yeah, that's interesting.
Okay. Okay.
I'll get some extras.
Yeah. Thank you very much. Okay. Thank you, Dylan. Okay. So we have these arrows here. This indicates that this flow, the value for this flow, depends on this parameter here. Note it's connected on both sides. It's indicated via the green, and on this stock here. So we have here this flow being given by weight in kilograms times energy expenditure coefficient. Okay? So with that in place, I would like you to set the initial value associated with the weight in kilograms to be 75 kilograms. Okay? 75 kilograms for the initial value of weight in kilograms. Okay, so ladies and gentlemen, I would like you now to go and I would like you to put in place, okay, I'm getting confused here, but okay.
Testing. Hello, everyone.
Thank you, Dylan. Thank you. Okay, now we're going to put in place a mechanism whereby energy intake will depend on the energy from food that someone has consumed. So we will go drag a variable from the agent palette in here, and it will be called energy from food. Okay, energy from food. Okay, thank you, Dylan.
heard my delightful test message come through.
Indeed, I did. Okay. Thanks very much. That's very handy. Okay. So, the energy from food here will be dictating the energy intake. And so, with energy from food, I'd like to go to the link and establish a link from the System Dynamics library between energy for food and energy intake, ladies and gentlemen. There we go. And energy intake. And the formula for energy intake, ladies and gentlemen, will be given simply by energy from food. Okay. Having done that, ladies and gentlemen, I'd like to set the initial value for energy from food to be 1.2. Now, I have not attempted a serious energy unit analysis of this. I should really do so. I apologize, I don't have that in place for you for this time. So this is going to be a sort of a rate associated with energy from food, a number of perhaps kilocalories per day or kilojoules per day of intake. And it's going to go into energy intake, and that will contribute, although probably with some coefficient, giving the amount of weight per kilojoule into a weight in kilograms. Okay. It's a complex process here. The point is we could substitute this with a very physiologically grounded model where all that analysis has been done. And there are such models. I just want to give you the general gist here. Yes?
Do you need to define energy intake equals for that flow?
So I said, I thought I said it, but I didn't do it. Thank you. Energy from food. That's what it is. Thank you. Yes, a beautiful example of how showing this link indicates clearly it should depend on that, and you could spot, wait, there's something missing. Okay? It's one of the virtues of having this. Okay, so ladies and gentlemen.
So one of the questions is, the energy from food is obviously it's a variable and it's set at 1.2. Why is that not a parameter? Is that not an underlying assumption?
Because we're going to be changing it.
Okay.
It'll be a variable because it will vary. And in fact, we're about to vary it. Great question, but let's vary it, okay? Okay, so ladies and gentlemen, to vary energy from food, let's go down to the place where people eat. Where do people eat in this model? Anyone remember? Sorry? Where do people eat? Do you remember where people eat? Ladies and gentlemen, where in fact do they eat?
Eat events, eat.
Yeah, so eat a convenience store meal, eat a supermarket meal. And again, this really needs to be done on a clearly energy per unit time basis and so on, and it needs to be tightened up a little bit on this, but eat a convenience store meal, we're going to set here energy from food equals 2.4. Okay? For eat a supermarket meal, energy from food equals 1.5. It's really energy per unit time because it goes into flow. And anyway, eat a convenience store meal, again, it's 2.4. Eat a supermarket meal, it is 1.5. Okay. Now really I should have done that with constants, having nice constants, but in any case, we have that here. So when they eat a supermarket meal, they're getting less energy than when they eat a grocery store meal. Okay? I apologize for the abuse of units here. As I say, I need to tighten this up and probably do a mass balance type of analysis on this. And that I will do, although I'm tempted to put a Kevin Hall's model and have a full richness of evolution of weight accordingly. Okay, ladies and gentlemen, are you feeling comfortable with that? How many people need help? Would people like some help? So what did I do? I went down here, and for each of the places, there's two places that says eat a convenience store meal. For those, I just added this line, energy from food equals 2.4. For the places where it says eat a supermarket meal, I set energy to food to be 1.5. Okay? Who would like me to show something? So again, what is this energy from food? It's this variable that we added. And it will vary. It will vary every time we eat. It'll be providing us with a certain amount of energy per day for that period. Energy density, sort of at that period of time. If we eat something healthier, our energy consumption is going to be lower than if we eat something that's more energy rich with fats and sugars, such as we might get from a convenience store, such as we might get from a corn dog of North American infamy. Okay? Do you have corn dogs here?
Yeah, they're called Pluto pups.
Pluto pups.
Yeah.
Okay.
Battered sabs.
Battered
Sabs.
Battered sabs.
Sabs, S-A-B.
Sabs. Okay.
We have hot dogs.
I'll take your word for it. You do have hot dogs, and probably there's those are well established in North America for sure, and I guess probably they have the European ancestry, right? To some degree with the kielbasa. But I'm sorry to hear that there's battered sabs and Pluto pups. I only learned myself from those with younger individuals and their family about pizza pops, which apparently are quite dangerous. Okay, so ladies and gentlemen, what's going to happen here? I'd like to, because I haven't had a chance to really explain system dynamics to you in a clear thought. What's going to happen here, ladies and gentlemen, is you recall that this energy outflow, this exhibits what's called a first order delay. So this energy outflow, this basal energy expenditure, it depends on two things: weight in kilograms times this energy expenditure coefficient. Okay. Now this stock, you can think of it like a bathtub. There's water coming in and there's water going out. There's energy coming in and energy going out. Okay? A rate of energy of intake and a rate of energy expenditure. Now, if the rate of intake for your bathtub is greater than the rate of outflow, what's going to happen to the bathtub level? It's going to rise, right? It's going to go up. If the rate of energy intake is less than the rate of energy expenditure, what is or correspondingly to the bathtub, if your energy intake exceeds your energy expenditure, what's your weight going to do? It's going to go up. And as it goes up here, your energy expenditure will rise. It's going to go up until the point where it's no longer changing. It's not going up any further because energy intake equals basal energy expenditure. The rate of energy coming in equals the rate of energy going up. Your weight's going to be constant. So if we have a higher energy intake than our expenditure, our weight will rise and stabilize at that level where it's in balance. By contrast, if our energy intake is smaller, if we switch our diet so it is smaller, our weight, our energy intake will be less than our expenditure. Expenditure being given by weight in kilograms times this. So for expenditure, if our weight is very high, expenditure will be high. And as a result, the inflow will be less than the outflow. And when the inflow to your bathtub is less than the outflow, what is the bathtub going to do? The inflow is less than the outflow. The water's rushing out and water is just trickling in. What's the bathtub going to do? It's going to go down. So that's what's going to happen. If we put these people on a diet, their energy intake drops, their weight will drop. It will drop until expenditure equals energy intake. So this is a regulatory system, and system dynamics excels at representing regulatory systems involving continuous quantities like stocks. In this case, it's a weight. It could be a risk perception. It could be a perceived sort of weight, a target weight to which people aspire. It could be a sort of sense of what a normal energy intake is. It could be a perceived quantity or an actual physical quantity. It could be a target of some sort. But the point is that when we have a regulatory system, it will sort of get itself into balance here. So if energy intake is smaller than weight, our weight will drop until the two are equal. Energy intake is higher than the expenditure, the weight will rise. Okay? So do you want to see this? This is ready to go. You want to run it? Okay, let's run it. That was a muted response, but I took it as a yes. Okay, so let's run this thing. Now, system dynamics does have an impact on the running time. And maybe in light of this, actually, ladies and gentlemen, I probably should have done this, and I apologize. I'm canceling out of that and going up to the model as a whole. One of the things you tune with system dynamics is its level of time accuracy. So if you go to the model as a whole and you go down to numeric methods of the model, when we've looked at the model as a whole, we've done it mostly to look at the time units. But if you scroll down, there's a lot of things you can specify. Here, for those interested in Java integration, you can specify external libraries. These are Java so-called jar files, which let you use literally hundreds of thousands, I would guess millions of libraries out there, things you can use that are created in Java to do everything from GIS to database access to contact over the network, reading in weather information from services, going and looking up information, etc. Java's visualization, all sorts of stuff. Numerical methods, however, is what we want to focus on. There's a thing called a fixed time step here, okay? And I'd like to change this to be 0.01, okay? Actually, even doing 0.1 is enough, I think. 0.1, okay? .1, are we okay with that? Is Dylan out of the room? Okay, 0.1. Who needs help? Help, okay. Help is on its way. Ladies and gentlemen, are you ready to go? Okay, let's run it. Let's take it for a spin. Okay? The feedbacks will be taken for a spin. Okay, ladies and gentlemen, we have our normal pause as it figures out some routing, and then let's speed this thing. Oh, yes, okay. Well, yeah, we'll come back to that. So, ladies and gentlemen, here it's engaged in some pondering. We're going to go down to the level of the population, and here we're going to see a person's weight. And that person's weight will be evolving over time, okay? Taking some time, and I think it's because of the GIS functionality here. Okay. Although, going unusually slowly. Okay. Okay.
So,
Yes.
interruption. Want to make a comment. Whenever you see something is used but not expected, the first thing you want to check is in your visually looking at all the links. So sometimes it's finicky that the ends are showing as pointed to something, but it's actually not sticking to it. And so that's just a top thing to check whenever you see the error message being something is
Thank you.
used but not expected.
Yeah. Okay.
So I saw like 4 incidents of that.
Okay. Yeah, this model is going slowly, and so I do want to try to diagnose the performance. It is possible it's AnyLogic's sort of use of the GIS, but it's going a bit slower than I would have thought, and but I remembered certainly. So I just want to run this thing and see if I maybe if I tuned another setting, if it might might help with this. Okay. Hey, come on over. Okay. Okay. Now I'm going to go down to the population. Here we go. Okay. Okay. Still going very slowly, which is surprising to me how slow it is. Okay. Oh yeah, it is communicating over the network, so it's probably trying to figure out the routes to the appropriate things. Okay. Okay, now it's going faster, but still not exactly roaring along. Okay, so this is a person whose weight, for example, is rising over time. It started low. Their energy intake is evidently exceeding their energy expenditure. And once again, AnyLogic is taking some considerable time to access the database. So I think all of us are hitting it at once, and unfortunately, the network here is, as I know from uploading videos, is not the speediest. Okay. So here we're getting some dynamics associated with each individual as it runs, weight dynamics and decline in weight as they are seeking food and consuming meals here.
Now, can I just ask that system dynamics part of the model is pointing at averages, is it? So it's for the population rather than...
No. Okay, so great question, Colin. So system dynamics has most traditionally been used in health for populations, that is or subpopulations. So you have an aggregate model, and the traditional way to do that is you would divide the population, perhaps stratify it into 5-year age categories and sexes, perhaps maybe ethnicities. But within each group, you're going to be dealing with averages typically. And that has real challenges associated with it if you're dealing with a situation where there's pronounced heterogeneity and where that heterogeneity is likely to matter, or where you need network information and information associated with spatial context. In this case, what we've done is a hybrid model. So with each person, we have incorporated within them a representation of their metabolism using system dynamics. That is not in any way aggregating over the population. It's specific to that person. The system dynamics as a method characterizes feedback-based systems and accumulations. It's not in any way specific to only be used for aggregation. It's just aggregate models. It's just that's how it's most traditionally used. You most see it most commonly. But here we have used it to characterize within a given person their particular weight dynamics. And it is very specific to that person. Here, is it aggregating? Yeah, it's aggregating over their sort of the weight in their body, but that's purely within an individual. So is that helpful? So you can use system dynamics at an individual level. It's just that it's somewhat less common than using it at an aggregate level. Jeff, do you want to say anything about that?
I think of it as, it's kind of the law of mass action, and you're really thinking of, you've got cells in your body or molecules of hemoglobin, so it's the same sort of thing. And again, it implies the law of mass action plus perfect mixing.
Right. And in this case, within the body, within a
the
single
body.
human body.
Yeah.
So system dynamics, is commonly associated with aggregate models, but it can be used and very fruitfully is used at an individual level. And in fact, going back 8 or so years, we've been working to characterize, for example, immunological dynamics within an individual using system dynamics. There's theory for doing that. Same thing with physiological models. Very, very rich to do. And I know this is an area where Ross Hammond has also done some work, because it provides an exquisite way of characterizing dynamics associated with feedback systems, particularly for continuous variables like weight, risk perception, aspects of sort of strength of belief, aspects associated with an individual's sort of immune strength, other quantities that are conceptually continuous. We can capture their dynamics very, very well, and the regulatory processes which operate in them and keep our bodies in balance. So that's what this is depicting. Is that helpful as a comment? You will notice that each person here is going to differ in terms of their weight. So that person, for example, was squarely at around 75 kilograms. This person is up around 79, but you'll notice they're exhibiting weight dynamics as they eat different balances of meals. This is a heavier individual also, and this one indeed up near 95 kilograms. So these individuals are exhibiting weight change, and that weight change response is a reflection of their eating behavior, and their eating behavior in turn reflects their food environment. Okay? It reflects what's in their larder. So this person exhibits some weight dynamics here. Are you seeing things like this? Okay. So we have a little simple theory of kind of weight here, which is a reflection of the fact that we do have some very codified theory of weight change from very detailed experiments conducted in laboratory studies associated with how human body composition and weight varies with energy intake and expenditure. Okay, so if you folks are okay with that, I would like to go on to one final component. Any questions about that before we go on to one more issue here? Are you okay with that? Okay. So, ladies and gentlemen, I would like now then to go on to. I'm just looking at this, right? Okay. Yes. Okay. Excellent. 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 So, ladies and gentlemen, I would like to go back to. Excellent. Okay. I would like to go back to our start this morning. I would like to go to main, and once again, I would like you to engage with this map. We're going to add parks into the map mix, okay? But before we engage with the map, I would like you to add to this model a representation of parks, okay? So I'd like you to right-click. Oh, I'll save this as version 4 now. Okay, version 4, and I will indicate it in days, and I will go stop.